Now you can ask me, so why is that high strength bars and high strength steel is used for prestressing? Why not we can use your regular normal reinforcing bar for prestressing? That's what people attempted in the olden days, but they were finding that the amount of prestress that it was locked, it was not available over a period of time. So there are a lot of losses. So that losses were mainly because of the shortening that is happening from creep and shrinkage. Typically, they measured that it is about strain of 0.0010 strain. Now, if I am using a normal steel for prestressing, let us say if you take Fe415 or Fe500, what is the yield strain for Fe415? You can see 415 divided by 2 into 10 to the power 5. So, if you look at that yield strain, okay, which will work out to be 0.00207 or something, right? And if it is going to be 500, it is going to be 0.0025, right? So, the values will change, but let us say Fe415, right? And when I do prestressing, I cannot go more than the yield, right? Because of the external loads, again more strain will come. So, typically we take that as 2/3 of the yield. So, 2/3 of 0.00207 roughly works out to be 0.0015. So, that is the maximum strain that I can apply if I am using normal prestressing, normal reinforcing bar for prestressing, right. So, you see here, now this is the maximum that I can put. Now, we have seen that 0.0010 will be lost due to losses. So, if maximum I can put only 0.0015, if that in that 0.0015, if 0.001 strain is lost, now how much will be left with? So, we are saying that 2/3 of prestressing strain, that means 0.001 by 0.0015, this is the possible, maximum possible. If I am using, if normal steel is used for prestressing, right. So, if 0.001 is lost, then you see that about 2/3 of the prestressing strain is actually lost due to creep and shrinkage, so which is not good. So, that is the reason the earlier attempts of prestressing, they were not successful, and the elements were undergoing more cracking and more deformation, and people were saying that prestressing is not really working. Main reason was they were not accounting for the losses that is happening because of creep and shrinkage, right. Now, if I use high strength wire, we can go as high as 0.007, the initial prestressing. Even if let us say in this 0.001 is lost, still I will be left with 0.007 minus 0.006, which is 0.001, which is 0.006. Okay. So, we will still be having 0.006 of the prestressing, which is quite effective for putting compression on the concrete. So, that is the reason you have to go for high strength prestressing steel. If you use regular normal steel, then you cannot apply too much strain, and most of them will be lost due to shortening of concrete from creep and shrinkage. So, that is why the early attempts of prestressing, they were not successful. Okay, now relaxation, again we said, we have previously discussed. As you can see, in prestressing always we try to keep the stretching constant, right. Stretching means actually the strain, right. Now, what we are saying is the stress that is required to keep the stretching is always going to keep coming down because of the material behavior, which is called as relaxation. Now, if you take it, this is the definition: loss of stress at constant deformation limit is called relaxation. Constant deformation or constant strain, we can say, right. Now, what are the implications of this? You see here, I keep the strain constant, right. So, let us say I take here example, right. In this example, initially I kept it at this strain, right. So, let us say epsilon pi, strain remains constant, but now what we are saying is initially I am keeping this FPI or let us say FP1. Now, over a period of time, now I need to apply only FP2, which is lesser than FP1, to keep it at the constant strain. So, what is the significance of that? What is the definition of an elastic modulus? It is the stress by strain. So, in other words, this material is having only this much stress to keep it at strain, means effectively you can see here that the modulus EP effective is going to be less than the initial elastic modulus EP, or in other words the material is actually softening, right. The elastic modulus of the material is originally EP, but because of this process of relaxation it is softened to EP effective, which is less than EP. So, that is called relaxation, right. Now, how do we measure this relaxation? People have studied by doing some testing, by keeping the strand at particular strain, and they kept measuring what is the stress that is required to keep it at that constant strain. So, usually we do the testing for at least 1000 hours, and people have done testing on almost up to 100,000 hours, right. So, what they have found is, you see here different chart curves are here. In the x-axis you have time on hours where they have kept the strain. In the y-axis you have FP by FPI. So, FPI is your initial stress, how much that initial stress that I applied to reach that particular strain, and FP is the stress at any point of time, right. So, you see here this is the FPI and this is your FP, like what we have seen in the previous slide. Now, you can plot depending upon how much my initial stress that I am keeping, whether it is 60% of the yield strength or 70% of the yield strength or 80% of the yield strength or 90% of the yield strength. So, what you see here, if I keep the initial stress as 60% of your yield strength, I get this curve, right. So, you see here this is a nice curve that you get. And if my initial stress is kept much lower than the yield strength, what you find here is this is the original ratio. If this ratio, if it is close to be 100, that means that there is no loss, right, there is no loss. So, you can see for the violet color with when the initial stress is about 60%, you see that even at 100,000 the actual stress remained at about 95 to 96% of your initial stress. That means that relaxation loss is less when FPI by FPY is small. Let us look at the red color curve. The red color curve is FPI by FPY is equal to 0.9. That means the initial stress is 90% of the yield strength. That how we calculate yield strength we have seen. Roughly we take that as FP 0.1 K, right. So, that worked out to be around 15 something that we saw in the previous slide, right. So, if I am applying stress very close to that of yield, you will find that the loss in pre-stress due to relaxation will be quite high. For example, you see at the end of let us say 40,000. So, this is in hours, right. So, you get how much this is, roughly it is about, I can say 85% or so. This is about 85%. What is 85%? FP by FPI. Okay. That means I have lost 15% of the initial stress at the end of 100,000 hours, which is 1 lakh hours, right. So, that means if my initial stress is very close to that of yielding, the loss due to pre-stressing is going to be very high. So, people have come up with this kind of equation. So, now for any point of time t in hours, if I know the initial stress by FPY, then I can find out FP. So, that is a equation that has been developed for this family of curves. So, from our design also we can calculate, let us say I am doing the calculation at about 40,000 hours, right, at 40,000 hours. Now, I can go back, let us say if my FPI by FPY is 0.8, which is this black color curve. So, I go back and this is what we get, the loss in pre-stress. So, that equation will directly give what is that FP by FPI. So, with this we can do that. Now, what are the typical values of yield strength to ultimate strength? For low relaxation strand, it is high. That is what we want. We want always yield strength to be higher, as close as possible to the ultimate strength. Then I can apply for more pre-stressing. See, for design, our ultimate strength is not the criteria. We worry about the first point, the yielding. Yielding is our major limit state. We do not want the steel to reach its yielding quickly under service loads. At ultimate, it has to yield definitely. That we will discuss in the flexural design aspects. So, higher the FPY by FPU, the better it is. So, that is why if you look at stress relieved strand is having lower FPY by FPU, plain pre-stressing bar is also having lesser, And deformed pre-stressing bars, I said pre-stressing bars are also available for larger diameter. They have the least ratio of FPY by FPU. That means their yield limit is lower. If the yield limit is higher, which is better for us from design point of view, we can come up with a more economical design, right. So, now let us see how to, okay, there are different design stress strain curves of pre-stressing that we talked about. Now, Ramberg-Osgood model is very commonly used to simulate the actual stress strain curve. This is the actual stress strain curve of pre-stressing steel, actual stress strain curve. What is the meaning of actual stress strain curve? When I test it in the lab, this is the kind of stress versus strain response that I will get. Okay, maybe this is a good opportunity to put FP for pre-stressing and epsilon P for strain in pre-stressing steel. So, you get this kind of a curve. Now, how do I come up with a closed form equation? See, for me, when I want to put it in an Excel or a MathCAD sheet or a MATLAB program, if I have a closed form equation, it is easy for me to calculate the strains, right. So, how can we idealize this particular curve, right, what you have, into some kind of an equation that which is possible, right. So, that is what we are looking at. Okay. So, somehow we have to idealize them into equations. So, the first step, so these are the parameters that are there. Fp is the stress in the pre-stressing steel at a specified strain, Ep is the elastic modulus of the pre-stressing steel, epsilon Pf is the strain in the pre-stressing steel, and Fpu is the ultimate strain, So, this should be epsilon Pu, sorry, epsilon Pu. So, this is your epsilon Pu, okay, and this is your Ep, and this is your stress, and this also, let us say we will take only epsilon T, right. Now, this can be idealized by these two curves. So, first thing what we do is we take these two curves as first you make it like a bilinear curve like this, two curves, this slope you know and this slope you know, right. So, the actual curve, this black color curve is your actual curve. The actual curve is converted into two linear curves, okay, and they are going to intersect. For example, from here, from the actual curve, I can directly calculate my Ep. If I take 2 points here and here, if I take the slope, I get my elastic modulus. So, from the actual curve, I can get Ep easily, no problem, right. Then I know from this linear curve, if I can measure this, then that slope will be equal to A into Ep. From here, I can get what is A. I can get what is A, right. Now, this two lines, now that I got the A, wherever this is going and hitting this point, that stress Fp is equal to 1 minus A by B into Ep. Now, I got Ep, I got A, I have to find out only this B. Now, this is a simple linear equation. So, at what point it is going to go and hit the y-axis, I can get the stress value. So, this is given to me, this Fp value is given to me. So, using that and calculated Ep and A, now I can calculate what is B. So, I have A, I have B, I have Ep. Now, only thing that I do not know is what is C. So, the C is nothing but it defines the sharpness of the transition from linear to nonlinear behavior. So, for example, this is what it is. So, whether this curve is going like this or going like this or going like this is what it is given by parameter C. I can calculate A, I can calculate B, now I have to calculate C. So, that what you do, you get your experimental data. So, once you calculated A and B, now you try to match the experimental data by varying different values of C, and you select the C's that will closely replicate the experimental measurement. In that way, you get all the parameters A, B and C. So, that is what we have. These are the estimation properties. So, this model, it gives an accurate representations of stress strain response of pre-stressing strand, and this is the modified Ramberg-Osgood formulation. So, this is what it is. First step is we represent the actual stress strain curve into two straight lines connected by a curve like this. Okay, this is one line and this is another line. Okay, so that's the first step. Next step is from here. slope I can calculate EP, okay. So, that is what it is. EP I can calculate, then as I explained you, from this slope again I can calculate what is A, and then point B, basically this FP, the stress FP is nothing but this point, okay. Let us say FP at A, this FPA is given by this. So, from EP I know, A I know, then I can find out what is B, because it is a simple linear equation, right. So, we can find that. Now, the next is find C by trial and error by matching that with the experimental data. So, that will help us in typically a high value of C will result in abrupt transition, it will not be a smooth transition. So, you have to select appropriate value of C. So, once you find A, B, C and parameter, now you have a one beautiful equation like what we have given here. So, that will replicate the entire response. Now, for any value of epsilon P, I can get my stress in the prestressing steel, right. So, this is the beauty of this equation with which we can calculate now what are the entire response of prestressing steel. Now, quickly what are the thermal properties? We know that steel cannot take temperature, and anything if you measure that steel temperature goes more than 300 degrees centigrade, there will be a substantial reduction in strength and stiffness. So, that is why your cover for the reinforcement makes a important parameter. So, you need to make sure that you give adequate cover, because concrete is going to protect the steel from reaching that particular levels of heat. So, we have to keep that in point. So, when we design from fire resistance point of view, always we have to ensure that if the temperature has gone more than 300 degrees centigrade, then we typically ignore them their contributions in capacity calculations. Now, bond is also very important, especially for pre-tension members. Then you don't have anchorages, the anchorage is happening only through bond. So, you need sufficient length before which it can transfer the entire force, right. So, it can take the maximum force. So, that length is called transfer length. Usually we take that as minimum as 30 strand diameters. If you are taking about wires, then the transfer length is about 100 wire diameters, right. Now, we also have different permissible stresses are there, right, in prestressing steel. Now, when you do the stretching, origin initial stretching, we cannot exceed 76% of ultimate strength. This is what IS 1343 code says. I cannot go more than 76% of your ultimate strength. So, ultimate strength FPU is how much? We have said it is 1860 megapascal. So, I cannot go more than 0.76 times 1860 while I am jacking, okay. And then final stress after allowing for all the losses again cannot be less than 45%. So, the stress always has to be between 0.76 FPU and 0.45 FPU, okay. So, this is the range acceptable level. You cannot have too high losses also, again you cannot apply too much pre-stress close to that of your ultimate strength as well. So, these are some of the ultimate strength and elongation values that are given for different cold drawn stress relieved wires as per this IS 1785. You see 2.5 you get higher strength, lower the diameter you get higher the strength, okay. So, typically what we use is a 7 millimeter wire or a 5 millimeter wire in our pre-stressing applications, and you get for the strand we get a higher wire diameters, okay. Sorry, typically we try to use this 3 mm diameter wires, okay, and you get these are the minimum elongation also that is recommended by this IS 1785. Okay, so let us summarize what we have discussed in the module. We have discussed the various types of pre-stressing steel, starting from wire and then strand, and then we have tendon, then we have cables, right, and then we have discussed the mechanical properties of pre-stressing steel. Again, the elastic modulus does not change, but however the yield strength and ultimate strength will increase depending upon what type of pre-stressing steel that you are going to use. But most important thing is the strain at failure is going to come down, right. And we also discussed the production process of pre-stressing steel, and we have discussed relaxation loss, particularly this is the relaxation loss that we talked about, okay. And if you are using low relaxation strand, which is better, the loss due to relaxation will be less. And we also explained how to use Ramberg-Osgood model for predicting the entire stress strain curve of pre-stressing steel, right. So, with that we are completing this first module. Thank you for your patient listening. I am looking forward to seeing you in the future modules. Thank you.